This is the screencast for section 6.2, example 9, that absolute value again. So you may predict that we are going to take the integral and use natural log, so we have that absolute value involved. We're also going to use some substitution, and because we have a definite integral, we're going to have to change the lower limit of integration and upper limit of integration to suit our u of x function. Alright, so looking at this problem, I have x over x squared minus 4. Alright, so a composition function, yes, you can look at it as 1 over u, maybe, where u is x squared minus 4 because the derivative of x squared is 2x, and then that relates to the numerator x by a derivative. So let's take our u and make that the denominator, x squared minus 4. And remember, that's a function of x, so we're going to have to change the lower and upper limits of integration. Now take the derivative, and we get 2x, so solve for dx for our substitution purposes, and we get du over 2x. So let's plug all that stuff in. The denominator turned into u, and then dx, we're going to use this expression, du over 2x. Now the lower limit of integration is not 0 anymore. 0 was meant to plug into x. Now we have u as our variable of integration, so we're going to take u of 0 as our lower limit and u of 1 as our upper limit. Alright, so now the actual x's cancel out, and I have a 2 in the denominator, so the 1/2 can come outside the integral. And I have, again, there you go, 1 over u du, so we're definitely going to use a natural log here. Now, the lower limit u of 0 is 0 squared minus 4, so negative 4. And then u of 1 is 1 squared minus 4, so negative 3. Now our lower and upper limit are ready to get plugged directly into u. So let's take the antiderivative, and we get 1/2 the natural log of the absolute value of u. And you can see where this is going to become important now, because negative 4 and negative 3 would not be able to get plugged into the natural log without that absolute value. And the thing is, if that would cause something that's undefined, the original problem, plugging 1 in for x or 0 in for x, was not undefined. So we can't let our work get in the way of finding the answer. We have to use those absolute values so that we don't create any undefined situations that shouldn't arise. So let's plug those in. Now I left the 1/2 on the outside, and then I took the natural log of the upper limit of integration minus the natural log of the lower limit of integration. And then that would be, without the absolute value, just the natural log of 3 minus the natural log of 4. And then a log property would combine that into the natural log of 3/4 with the 1/2 coefficient on the outside. The now try problem number 63 says make u substitution and integrate from u of a to u of b. So we have the integral from 1 to 2 of dt over t minus 3. I might want to put the dt off to the side so I can see that that's 1 over u, u being t minus 3. So I'm going to set that up and take the derivative, which the derivative of u is just 1, which means du is going to equal dt. So that's like a direct substitution. There's no fancy cancellations or anything that we're going to have to do. Alright, so we put in our substitutions. U is t minus 3 in the denominator, and then dt is du. The lower limit then is going to be u of the lower limit, old lower limit, 1. The upper limit is u of 2. Which that means then the lower limit is going to be 1 minus 3, which is negative 2. And the upper limit is 2 minus 3, which is negative 1. Now we have a simple antiderivative. The antiderivative of 1 over u is the natural log of the absolute value of u. And again, we have negative limits of integration, so the absolute value are very, very important. So I'll plug those in using the fundamental theorem of calculus part dos. And then I can use my log properties and get that that's the natural log of 1/2 absolute values, and then subtracting 2 logs turns into division of what you are taking the log of.